Welcome back, Contemporary Math. We are in Chapter 7C. This is called the Law of Large Numbers. So we are still talking about probabilities here. And they want to talk about the Law of Large Numbers. So they give you the Law of Large Numbers, or consider an event A with a probability P of A in a single trial. The Law of Large Numbers holds that for a large number of trials, the proportion in which event A occurs will be close to the probability, or P of A. The larger the number of trials, the closer the proportion will be to P of A. So what they're saying on this thing is that if we had a sort of graph, right? And this would be the number of trials on my x-axis. And if I want to do a coin flip, so I could do maybe the probability of heads over here. And so I'm conducting an experiment. We know our probability is going to go up to 1, and 0 is there. We know the ideal probability, the theoretical probability of getting a heads is going to be 0.5. So ideally, we would want this coin, if it's a fair coin, to be somewhere right along. We get a few trials. So let's say we flip the coin, it lands on head. If we flip it once and it lands on head once, it landed on heads 1 out of 1. We flip it twice, let's say we get 2 heads in a row. Guess what? My probability is going to be way up here. Now I do it 3. So it only lands on heads 2 out of 3 times. Let's say it lands on tails this time. So we can do this with a coin, trying the relative frequency. Now I think I'm going to be somewhere around 0.6. So my probability is looking something like this. Okay, but lands on heads again, so 3 out of 4, it's going to go back up to like 0.7. Come back up. But what we're saying is that as we go out to infinity, as we get a substantially large number of trials, this thing should be bouncing around 0.5. It should be really close to 0.5. And ideally, the more trials we go, the closer to 0.5 this thing should become. We could do the same thing with a roll of a dice. So if we want the probability of getting maybe like a 3, the probability of getting a 3 on any one roll is going to be 1/6 or 0.166. Repeating. So again, we're going to go from 0 to 1 in our probability. And let me just guesstimate maybe 0.16 is around like right in here. And so what we're saying is we're going to roll. And so if we roll our die a few times, we probably won't get a 3. We might get 2 of them. If we don't get any 3s, our probability is just going to stay here. We're not getting anything. The second we get a 3, I get a quarter, so it's going to be 0.25 somewhere here. What's going to happen is early on, I'm going to have a lot of movement in this graph. So 1 head is going to bring it up quite a lot, or 1 3 is going to bring it up quite a bit. And maybe I can get a 3 on my next one, so it's going to bring it quite down. It's going to wiggle quite a bit, and it's going to stop wiggling so much. It's going to kind of even itself out a little bit more. Each trial is going to do substantially less and less movement for this graph. We're dividing it by a larger number. Each subsequent trial is going to make it move a little less, and this thing is going to be winding, and it's going to be winding itself all around this 0.16. And ideally, the more trials I get, the closer to this true value of 0.16 repeating I will get. How close do I need to get? And how many trials do I need to do? that is something that is like one of those sort of discretion calls, right? Am I doing like heart surgery or am I throwing hand grenades, right? Do I need something really specific? How accurate do I need to be with this number? And so a lot of things, and to be honest, a lot of things in statistics are kind of sort of judgment calls like that. It's like, how accurate do we need this sort of thing to be? What sort of accuracy do we need, right? So you don't always need the utmost accuracy on everything, right? Okay. With that said, there's that saying, there's lies, dirty lies in statistics. I had an English professor that said that you could lie with statistics, and I know I'm being like a really nitpicky sort of on the language, but to me, like, you cannot lie with statistics. Numbers don't lie, right? A lie would imply that something is a false statement. And so I wouldn't say that you can lie with statistics, but I would completely agree you can absolutely mislead people. You can look at the wrong numbers, you can cherry pick things. The numbers don't lie, people misinterpret them, was what we always used to say. As a sort of retort to that phrase. But with that said, the way that you keep from misinterpreting statistics is that you learn better statistics. You learn what people are doing when they're doing their statistics, and you learn whether what they're doing is valid or not, right? There are valid things to do and valid sort of things to look at in statistics. And with that said, the law of large numbers basically says as we get enough trials, our relative frequency should be approaching our theoretical probability. If things are even, if we have a fair die, if we have a fair coin, they should be reaching that 1/2 probability or that 1/6 probability. Okay, so now we have an example. We're going to play some roulette wheel. So the roulette wheel consists of 38 numbers. There's a 0 and a double 0 that are green. Those are kind of the odd guys. There are 18 that are white. I'm sorry, not white. There are 18 that are black. There are 18 that are red. And so if we add them all together, we get a total of 38 different numbers. So we want to know what the probability of getting a black number on any spin. So if we want the theoretical probability here, we want the total number of spaces would be 38. And we want the occurrence of or a black number. And so there are 18 black numbers out of 38 total. We can reduce this to 9 over 19. 0.47368, I think is what I'm getting. 0.473. Run a little space. I think I did it. So 9 out of 19 gives me 0.47368. So what does that mean? The probability of winning when you bet on black is going to be around, what, 47%? So you should be winning 47% of the time. So now they want to know, if we spin this wheel 100,000 times, how many of those times would we win? So we should be winning an average of 18 out of the 38 is what I'm saying. And now we want to know, well, how many of those out of 100,000? There are a few different ways to figure this out, but they're asking the equivalent fraction here. So if you wanted to do butterfly method, that would work. 38x equals 18 times 1,000. Another way that you can do this, if you do the butterfly method, you might end up realizing we're solving for x up here and we're dividing x by 100,000. Another way we can do this is take that 18 over 38. And if this is dividing, we want to multiply. So if we take our probability and multiply it by the total number of times that we're doing this, we should get 7, 3, 6, 8. Or we're going to win 18 out of the 38 times, and we're going to do it 1,000 times. So we should be winning a total of 47,368 times. Okay. And this is if we do it enough times, right? If this has to do with the large of law numbers. So we need a large number of trials for this thing to be true. And if we have a large number of trials, on average, we will be winning 18 out of 38. So if we do a small run, we could spin this thing 5 times and we could get like 5 reds in a row, never win a black, right? But if we do it 100,000 times, if we do it a couple thousand times, we're expecting it to be pretty close to this 18 out of 38 thing here. And so we want to talk about the expected values, the next thing that we're going to talk about. And so we would expect to make $47,368 on this. If we spun this thing, we wouldn't make that much. We would win that many. Sorry, said that wrong. We would win this many times if we spun 100,000 times. So you might figure out we're spinning 100,000 times. We're losing more than we're winning, right? 50K would be the middle, right? Would be winning half the time. We're definitely not winning. We're definitely losing more than we're winning on this, which should make sense. The casino's in it to win. So I want to imagine a game. How do we figure out how much we're going to make on average per game? So imagine you're playing a game. Your friend rolls a dice, and every time it lands on a 3, you win $1. So we're going to play this over and over again. We're going to play this 1,000, 1,000,000 times. We're going to play this a ridiculous amount of times. That's what's going to happen. But we want to know on average, how much do you win each time you play this game? So if we play this game, we're going to win on average, if we do it for a long time, we're going to win on average 1 out of 6 times that we play this game. And so you might figure out, if I'm playing this thing over and over and I'm winning 1/6 of the time, and I'm betting and I'm making $1 1/6 of the time, it's going to average out to around. And I'm only making money here. He's not making me pay money for the game or anything crazy like that. I'm just making 1/6 of $1 each time. Now, and this is over. You'll be making 1/6 of $1. Okay, so now you win $1 every time it lands on 3, 7, 5, and you lose $1 when it lands on 4. So over the long run, if it lands on a 3, I'll be making $1 1/6 of the time. If it lands on 7, I will be making $1 about 1/6 of the time. If it lands on 5, I'll be making $1 about 1/6 of the time. I'll be losing $1. I'll have to subtract $1 when it lands on a 4, which is also about 1/6 of the times that I roll. So if I'm thinking about this might be more simple if I say $1, and this is like you're gonna win $1 for every 3 out of the 6 sides, or you're gonna lose $1 for every 1 out of the 6 sides. Is another way to think about this. And if I think about this way, this is 3/6 minus 1/6 or 2/6. You're gonna be making around. Not too. Wrong number. This is 5. It's 1/3. You should be making around 30. And this is each game you're playing. It's going to average around 33 cents. So if we want to know about the value that we're going to make per game, the way that we do it, well, we call it expected value. So this is the thing we call expected value. Expected value is the amount that you're going to make on average for each game that you play. So they consider it with 2 events. We can consider it with multiple events like we have, but consider 2 events with each his own value and probability. The expected value is based on these 2 events. The value of the event and the probability of the event is the way that I did it. I did it backwards here. My value is $1. The probability I will get $1 is a 6. Same thing here. I get 1/6 probability for each of these sides. The value of the event is $1. Or I get $1 for 3 out of the 6 sides is another way to think about it. Which means I really get 2/6 of a dollar. Which means I'm getting about 33 cents per game. So you might also notice these are positive values for the game. It's also possible if we end up paying more money, right, that it might be a negative value. We might be losing money for each game that we play. And it says that we can extend this to any number of events. Basically, all we're going to do is how much are you going to make from that event times its probability. We're going to add that with however much you make from the event times its probability. So it's the value of the event times the probability of the event is the way that we're doing this. Suppose that $1 lottery tickets have the following probabilities and values. 1 in 4 to win a free ticket. That's worth $1. 1 in 20 to win $5. 1 in 1,000 win 100, and 1 in 10,000 win 1,000. What is the expected value of a lottery ticket? Discuss the implications. And note, you do not get back your dollar you spend on the ticket. If you buy a ticket, you spend $1 and don't win anything, you lose $1. So there are a few different ways to think about this. Some of them are going to be easier than others. On this one, I think it's easier to account for the fact that we're spending $1. So we're going to spend $1. If we are spending $1, we have to buy a ticket. There is how many different prizes? Free ticket is one of the prizes. Another prize we can do is $5 winning. We can do a $100 winning. And the last thing we can do is $1,000 winning. And so I want to think the value of buying a ticket. So the value of buying a ticket, if I spend $1, this is where you might have to be careful. If I spend $1, that is $1 coming out of my pocket. That is a negative $1. And the probability of that is going to be $1. So this is my value versus my probability is what I'm going to do. I'm going to find my value, my probability. I'm going to multiply them together, and then I'm going to add them down. So if I buy a ticket, I lose $1. The probability that I will lose $1 when I buy a ticket is 1 in 1. It is guaranteed that I have to spend $1 to buy the ticket. If I get a free ticket, the value that I'm getting from that is $1. I'm getting my $1 back, and the probability that I will get a free ticket is 1 in 4. I get $5. If I win $5, the probability I win $5 is 1 in 20. If I win $100, the probability that I win $100 is 1 in 1,000. And if I win $1,000, the probability of this guy is 1 in 10,000. And so I want to sum all these up. I want to multiply and sum these guys up. I'm looking along here. Minus 1 times 1 is minus 1. And this side, I'm going to add what is 25 cents. I'm going to add 5 20s and another 25 cents, I believe. 100 over 1,000 is 1/10, or plus 0.1. The last 1,000 over 10,000 is another 1/10, or plus 0.1. So I'm summing up these 5 numbers. You might notice that this is the thing that's counting as a negative. If I sum up these 4, I get like 0.7. So this was the thing that came from me spending $1 for the ticket. This is the thing that's mainly going to count against me when I buy a lottery ticket. And this is the thing that's going to be my reward or count for me. But if I look at these two, you might notice I get a negative number. I get something like negative 0.30. So what does this tell me? So this is going back to the expected value of a game, and I made the horrible joke, like the best game in the casino is the game where you put your $1 and get your 4 quarters back. But it is absolutely true to some degree because it has an expected value of 0, right? We're not going to win or lose money on that game. What this is telling me is that I will lose 30 cents per game. On average, I will lose 30 cents per game for every game. Is it possible I go in there, I go buy a lottery ticket today, and on my first lottery ticket, I win $1,000? Absolutely. But guess what? There's going to be a lot of other people that are losing money to make up for it. And when we average all our savings and all our winnings and losings together, it's going to average 30 cents loss for the person playing the game. So the lottery people are going to make 30 cents per game. The person playing the game is going to lose 30 cents per game. So sometimes you have to look at whose perspective you're looking at things through. I think for the most part, we start with doing things from the player perspective. And then I think in the last example in here, I think we do things from the house perspective. But this is telling me a negative 0.3. That means I'm losing 30 cents for every game I play. So would you play this game? Is it within your interest to play this game? It is not within your interest to play this game, is what this tells me. When I see a negative expected value, it means on average you're going to lose money if you try to play that game. It is not a winning game. We would say that this is not a winning game because you're going to, on average, you're going to lose money for each turn. Is it guaranteed you're going to lose money? No, right? And in the short term, you could absolutely buy a lottery ticket and win in the short term, right? Those things happen. But in the long term, so this goes back to that principle of large values, right? The law of large numbers. If we play this game over and over and over and over and over again, it's going to average somewhere to a loss of 30 cents per game. So if I play 100 games, right, I have to move this over 2 decimal places, I would lose $30. So for 100 games, you would be expecting to lose around $30. So the more games you get, the more you're going to be losing probably. So playing more games isn't going to solve that one, right? Each time you play is probably a bad strategy for winning. Example 3, we're at an art auction. You're trying to decide whether to bid $500 for a particular painting. You believe you have a half probability of reselling a painting to a new client in New York for $1,000 and a quarter probability for selling it in San Fran for $800. Otherwise, you can keep the painting, an option that has benefits but not monetary ones. You get to look at the pretty picture, but that's about it. We want to find expected value. We don't care about whether you're staring at portraits all day. We want to know about the money on this thing. What is the expected value of the $500 bid? So this, again, there are different ways to figure it out. I know sometimes people like to take 500 away from the 1,000 and do that by a quarter. Take the 500 away from the 800. There are different ways to do this. But the way that I'm going to do it and the way your book has it set up to do it is you can guarantee yourself, you will lose $500, right? Buy the painting. And then there's the LA, there's New York and San Fran. Sorry, wrong city. New York and San Fran. So I want to think about the value of the thing, and I want to think about the probability of the thing. So I'm going to lose $500. What's the probability that I will lose $500 if I buy this thing? The probability I will lose $500 if I buy this thing is 1. It is guaranteed you're going to lose $500. You're going to spend $500 on it. The New York person says he will buy it for $1,000, but you only got a quarter probability there. And then we have this San Francisco guy. Ooh, sorry, got the wrong probability. Read the wrong line. The $1,000 one says he has a half probability, so he's 50-50 on buying it. The San Fran guy says he's about quarter sure he'll buy it. And we want to sum these together. So if I'm looking along here, I see a minus 500 times 1 is going to give me my minus 500. 1,000 times a half is going to give me 500. Quarter times this is going to give me what? 200. So I think I'm coming up with a positive 200 in this scenario. Okay. So what does this mean? The expected value of this painting or of this bid, I can expect to make somewhere around probably 200 on this thing. So you should be making somewhere an average of about $200 on this painting is about what you can expect to make about on this thing. Okay. With this said, the law of large numbers, the expectation for our relative frequency to equal our theoretical probability only works in the long term and the long run. So the gambler's fallacy is that thinking that we're going to get this achievement and that we're going to get this achievement in the short term. So this is believing that we're going to get that probability in the short term. This may not be the case. So this is like I'm flipping a heads and tails coin. If I flip a coin, a fair coin, and I flip it and it comes up on heads, what, 9 out of 10 times? Can I say anything about that coin? So if I'm doing 9 out of 10 times, if I get 9 heads out of 10 total, there's probably not a lot I can say about the coin only flipping it 10 times. But if I get like what, 900 out of 1,000, right? The more trials I do and the further off this gets, this looks more suspicious than this one, is what I'm saying. It should be doing 500 heads out of, it should be doing 50% of this thing. In the short term, this really doesn't tell us anything. We could get 9 heads in a row. I could flip a coin right now. This isn't completely unheard of to get 9 heads in a row. If you get 900 heads in a row out of 1,000 total, then you could probably say this was unfair, right? You could start getting at this was unfair. Now, if I do like what, 9 million or something, and this is 10 million, is that what I'm doing? Then we can definitely start saying things are unfair, right? When we get to the millions. Can't say a lot here. We can start saying more here. We can definitely say more here, right? This is probably definitely an unfair coin. There's something really happening here for it to happen this many times and come up this many times. So the more trials you get, the stronger you get at saying whether things are fair or unfair, right? the longer we do things, the more they should start equaling out to their theoretical probability. That relative frequency should start becoming that relative the theoretical probability. Sorry. What do they say? A gambler's fallacy is a mistaken belief that a streak of bad luck makes a person due for a streak of good luck. So if we're getting 9 heads in a row, the next coin flip is still going to be a 50-50 shot. So that's another thing that people do in their head that relates to this gambler's fallacy. We can have streaks, right? 9 out of 10 heads isn't going to really throw things off. In the long run, this will still balance out. We will get streaks in the short term. Short-term streaks absolutely happen. It doesn't mean things are unfair. It just means sometimes you get a run in one direction. We get a run in one direction, but after we do 1,000, it might start to balance itself out. It should be 500 if we want it to be fair, right? This should be 5,000 if we want it to be fair. This is what we'd call fair, right? You are playing the coin toss game in which you win $1 for heads, lose $1 for tails. After 100 tosses, you are $10 in the hole. Because you have 45 heads, 45 tails, you continue playing until you've tossed the coin 1,000 times. So they're trying to get at the same concept I just discussed here. We're talking about 100 tosses versus 1,000 tosses, at which point you have 480 tails and 480 heads and 520 tails. Does the result agree with the larger law of numbers? Have you gained back any of your losses? And explain. So after 100 trials, what do we know? We know the probability of my heads is 45 out of 100, or we could say 0.45. So ideally, this thing would be 50%, right? This is what we're thinking. I want this thing to be 50%. Okay. And I'm $10 in the hole. All right, so let's think about what happens after 1,000 trials and compare that. So after 1,000 trials, my P of H is a 480 out of 1,000. So you might notice this is what, 0.48. So this is actually closer to our expected value or to our theoretical probability. But if we notice how much money we have, this is 520 minus 480, you're actually $40 in the hole. So you're actually more in the hole on this one. So even though you were more lucky, you were more closer to the probability, you ended up playing more games, which actually made you in the hole more, right? It gave you more of a loss overall. So we did better per game, but overall we still did worse because we did more games. Okay, so I have a few more examples about streaks. So there is something very, the casinos know these rules, or they know these principles, and they know human behavior quite a bit, right? And so when we get on streaks, when we start winning, we start getting the right chemicals in our brain, and we're like, ooh, this is a good thing that happens to me, right? So they realize this thing, and they put up flashing lights, and they do everything they can to try to what do I say? Get these endorphins pumping in our brain to make us think that we're doing the right thing, right? And so with that said, you really have to check kind of your impulses on these sorts of things, right? Because your impulse and your intuition is probably going to be telling you one thing on it when you gamble and do sorts of, if you gamble and do these sorts of things, your intuition is probably going to tell you sort of one thing, but your knowledge might be telling you something completely different, right? And so that's kind of the one of the important reasons why we go over this section is so that you're not just like blindly, intuitively trying to reason things, that you have some kind of way to reason things and realize what is happening around you, right? So casinos completely try to manipulate you on your like personal, what I want to say, on basically human behavior, right? Things that we all have in common that they know that we all do and that we all do horribly because we're all human. And they can basically kind of manipulate these sorts of things about you, right? So the popular casino game of craps involves rolling dice. Suppose you are playing craps and suddenly find you got a hot hand and you roll a winner on 10 consecutive bets. Is your hand really hot? Should you increase your bet because you are on a hot streak? So if I'm winning, am I going to continue winning is kind of what this is saying. Assume there's a 0.486 probability of winning on a single play, the best odds available of craps. So one of the things the book finds, and I think it's all right, it's probably what we need to find, is the probability of winning 10 hands in a row. And this goes back to those and probabilities. So we're going to win a hand, and we're going to win a hand, and we're going to win a hand. We end up multiplying this 0.486 10 times, giving me somewhere in the ballpark of 0.000735. And this is the probability that you will win 10 hands in a row. So you might notice this is a really, really low probability. So if you feel like you're lucky or like your hand is hot because you're doing something that's really hard to do, or not really hard to do, but really improbable, right? You might be correct there, but does it mean that you're going to keep winning? So you're increasing your bet, and you're increasing your bet with this idea in mind that you're going to keep winning because you've been winning, right? That somehow winning allows you to win easier on the next hand. If you start winning, you're going to continue winning. Absolutely, that is not the way things work, right? So despite this number, if we want to think about we got these 10 trials. Okay, so now I roll the dice on the 11th turn. What does the 10 trials previous to that have bearing on that 11th trial? Does it change the 11th trial at all? It does not. So the 11th trial, you still have the same probability of winning and losing each hand. So each hand independently. And the other side of that is 514. We do 1 minus 0.486. So 0.486 would be the probability you lose, and you have a little bit. Sorry, said that backwards. This is the probability you win. This is the probability you lose. Sorry, got my numbers backwards. But 486 is the probability you win. 51.4% would be losing. So there is actually a greater chance you will lose. Even though you're winning, it doesn't really matter. It has nothing to do with that 11th trial. So independently, you still have a 0.486 or a 0.514. It's still this split for each dice roll. Okay, so we have a similar sort of example for example 6. It says a farmer knows that at this time of year in his part of the country, the probability of rain on a given day is 0.5, or there's a 50% chance of rain. It's 50-50, it's going to rain. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because his region is due for a rainy day? So this is kind of the same thing. This is a winning streak. This is sort of like a losing streak, right? Losing streak as in he wants it to rain. He's not getting rain for 10 days in a row. So since he's on a losing streak, he says, I've been losing so many times. You know what? My luck has to be coming around, have to be rebounding sometime soon. So you might think this, you might think, well, we're doing relative frequency. Eventually it has to start rebounding, to even things out. It has to start rebounding in the long term with large numbers. 10 days isn't going to tell you squat, right? You can have 10 days of nothing but dry, right? And if we do that 0.5, what's the probability it will stay dry for 10 days in a row? It's something like 0.009766. It's really a small probability, but it exists, it happens. It is an occurrence out there. Okay, so even though this is the probability for 10 days, what about the 11th day? What is the probability that it will rain or that it will stay dry on the 11th day? So it is still on the 11th day, it's still going to have probability of the rain or dry each day. So each individual day is a 50-50 shot. It does not matter about those previous 10 days. Each day is still going to be a 50-50 shot of whether it rains or stays dry. So this has no bearing on the 11th day. Okay, so the house edge. So this may not be a big spoiler, but casinos are there to make money. They generally have the favors and the odds, right? They generally have the advantage of the odds. So gambling houses or casinos generally have games set up so that the house always has a higher probability of winning than the patrons. For any particular game, the house edge is the expected value to the house of each individual bet. So previously we were figuring out things from the gambler's point of view. Now we want to figure out things from the casino's point of view. So you have a game of roulette. It's usually set up so that betting on black is a 1-to-1 bet. That is if you win the same amount as the money that you bet. There is a bet on a single number that is 35-to-1, which means you win 35 times the amount bet that you win 35 times the amount that you bet if you come up on that single number. So find the house edge in the amount of money the casino should expect to earn if a patron wagers a total of $1,000 for A bet on black, and B for a single number. So A for a bet on black. So if I want to bet on black, and now I want to figure things out from the casino's point of view. So I'm going to have to flop some negative signs that I did previously. But if you are the casino, this person, they come in to play your game, you are guaranteed to get $1,000. They are going to wager $1,000. If we were the player, we would make this a negative $1,000. Now that we are the casino, we are getting this money. So this is the money we are going to get. We are guaranteed to get it, so there is a 1 probability that we will get it. We could lose $1,000. As the casino, we could lose $1,000. The player would be winning it, and the player would be winning this $1,000. We talked about this probability, but the probability of landing on a black is 18 out of 38. That's coming from the first example we did in these notes. And if I think about this, this is 1,000. And I'm going to subtract somewhere around 473.68 is what this is going to give me. And so as a casino, if a guy is wagering $1,000, I will be making around 526 of those dollars for each game that they play. So you might figure out we're making around, what, 52% for each game that they play, I think is what we're doing. So the house edge isn't very much larger than 50, but it is still larger than 50, right? All right, similarly here, they're going to pay $1,000 and we're guaranteed that they're going to pay $1,000. We can guarantee as a casino, we're going to get $1,000. Sometimes as a casino, we got to pay out 35 times that. So sometimes we got to pay out $3,500 and we got to pay out $3,500 if they land on a single number. So if they pick the exact number from the roulette board, and again, that would be 1 in 38. If they pick a single number, that single number is one option out of the 38 total numbers that are on the board. So they put all their money on a number. And if we look at this, I got to subtract 35,000 over 38, which gives me, subtract these two numbers, I should be making somewhere around 78.95. I realized I said something wrong earlier. This isn't 52%. I'm doing something weird in my head. This is the expected value. So we're expecting to make 526 and 32 out of 1,000 games. So what this actually means, and I probably should write this on here just so we have it. This means that we're making, if we think about this for 1,000 games, if we divide this by 1,000, what it means is we're making about 52 cents per game. And so the important thing to notice here is that from the casino's point of view, we're going to be making about 52 cents per game. From the patron's point of view, he's going to be, or they are going to be losing 52 cents per game. So I think the important takeaway here is that this number is positive. So it means the casino is going to take in money on average for every game that a person plays. So the casino, when you find the casino's takeaway, it should always be a positive amount. If you're doing a player at a casino, it should be a negative amount because they're going to lose money per game. And so this is what the casino really bets on. Like they're betting on that they're going to average 52 cents per game. That's not a lot of money per game, but you get people playing a couple games, this adds up really quick. And there could be a person that goes in there, right? They go and play the one-armed bandits or whatever, they hit it, and they hit it big on like their third one, right? They might walk out of there with $1,000, but guess what? There's going to be at least 10 other people that are walking out of there that don't want to talk about how much money they lost that night. So they are making it up somewhere else, right? The casino makes up money somewhere else. They're not in the business to lose money. Same thing with this. If we wanted to divide this by what? 0.078. So I guess I could round it to about 8 cents per game. They're not going to make a lot of money off of people placing these bets. They're going to make about 8 cents for every game that they allow someone to do this on. But they are still making money for each game. It is still positive. As long as this number comes out to be positive, a number larger than 0, they are still going to make money on that game. And 8 cents might not seem very much, but you do 100 games, that's already $8. You do 1,000 games, and you've already made $80 just off of a game, but sitting there. So they are definitely in it to make money, right? With that said, this is the final problem in 7C. So if we want to find expected value, it is the value times the probability, and we add the value times the probability. Same thing here. All right, see y'all soon. Take care. And don't gamble all your money away, right? I think is the moral of this story.
Don't go into a casino expecting to make money. There's a reason why they're in business, right? They understand statistics. They understand these expected values, and they understand their expected value as long as it's positive. It doesn't matter if they lose money on this one person. They have 100 other people playing 100 other games in there, right? They're going to make their money. You can take that money, you can take it away. There's other people that are going to put that money in. So it's not coming out of the casino's pocket, that's for sure. All right, stay safe. Take care and don't gamble away all your money.